So welcome. So this is week 1 of live session, Principles of Signal Estimation for MIMO OFDM Wireless Communications. And so in week 1, so I'll first start with a few brief summary, which I would like to give to you, and then we'll discuss the week 1 numericals. Okay, so I will be discussing the previous year week 1 numericals. So you will get some assistance to solve the current sessions numericals. So all right. So in week 1, we start with a IoT based sensor framework. Okay, so what is happening is that you have a sensor in a practical scenario. You have IoT scenario, Internet of Things IoT scenario, and you have the sensor which is actually trying to sense analog parameters. Right, so you have analog parameters like temperature, pressure, pollution, and so on. And you have a sensor which will try to sense these analog parameters. Now, we try to mathematically model this practical scenario, right? So we have this practical scenario, and this practical scenario we try to express it in terms of a mathematical model, which is represented as y is h plus v. Okay. Now here y is the observation at the receiver. H is the parameter which has to be estimated, and this is unknown. And V is the additive white Gaussian noise, AWGN, which is represented as N with mean 0 and variance sigma square. Okay. So what we are saying is that you have a practical scenario where an IoT sensor is trying to sense some information, some practical analog parameter, and you are trying to express it in a mathematical model. Okay, so this scenario can be visualized as a transmitter and a receiver, and the transmitter is sending some information to the receiver in a noisy medium. So for ease of understanding, currently we first assume that the signal which is being transmitted is not changing with time. Okay. So this is not time variant. Okay, so this is an assumption which we are taking. So assume that you are transmitting some signal at value h, and with time it is not varying with time, and it is being transmitted, and you observe some fluctuations. Right? These are the fluctuations which you are observing over time, and these fluctuations are random. Now this is an analog signal in nature, right? The signal which you observe is analog in nature. You sample it and you obtain some samples which we represent as y1, y2, and so on up to yn. So this kind of signal processing which we are trying to do is termed as batch processing. So in signal processing, we have two kinds of processing. One is the real-time processing and one is batch processing. So in real-time processing, what happens is, say you observe y1 and you try to estimate h for y1 itself, right? But in batch processing, you take few observations, right? You wait for some samples, n samples, and then you process all those n samples together as a single batch, So that is called batch processing, right? So what is my aim in signal estimation or parameter estimation? So my aim is to estimate the parameter which is being transmitted. So what is being transmitted here? I am transmitting H, right? So I am transmitting H and I am receiving some Y's, YK. Okay, I am receiving some YK and I need to estimate the actual original parameter H from these YK. So what do we have in hand? We have the Y's, we have the YKs. Okay. We don't have the true value of H, we don't know. So we'll try to predict it or estimate it or intelligently guess what is the true parameter. Note that these Y's which you are observing are subject to some noise, right? These noise are random in nature, but they have a known distribution. This is very important, right? So you know the distribution of noise. If you don't know the distribution of noise, then we can't estimate, right? So the basis of signal estimation or random signal estimation is possible because we know the distribution of noise. Okay. So we come back to the signal model, that is Y is H plus V, such that V is Gaussian distributed with mean 0 and variance sigma square. Okay. So first we try to find out the expectation of Y. What is expectation of Y? So expectation of Y, to find out expectation, we compute the expectation of H plus V, and expectation of V is 0, right? This is given to us, and H is not varying with time, right? H is a constant, as you should remember this, right? H is not varying with time. So expectation of H is H itself. So we get that expectation of Y is H. Further, variance of Y. Okay, so variance of V is sigma square and variance of H is 0. Since H is constant over all time duration, hence the H is not varying at all. So variance of H is 0. So we can say that variance of Y is 0 plus sigma square, which is sigma square itself. Thus, Y has a Gaussian distribution with mean H and variance sigma square. Okay. Now, very interestingly, if you subtract H with Y, right, so you get a Gaussian 0 comma sigma square distribution, which is V itself. So what we say is Y is nothing but a mean shifted Gaussian, right? So the mean is shifted by value H and it is Gaussian distributed. The variance of Y and V are same. They only differ in the mean, right? So this representation of Y can be expressed as the PDF, the Gaussian PDF. So 1 by under root 2 pi sigma square exponential minus Y minus H square over 2 sigma square. So this is the mathematical PDF of Y. And note, now we are going to analyze it. So far, this PDF of Y, this is the PDF of one sample, only one sample, Y1 or Y2 or YA, general Y or YN. Okay, so this is the PDF of by k, where k is between 1 and n. Okay. Now, if we have multiple time instants, okay, if we have multiple time instants, please mute yourself. Okay. If we have multiple time instants, say y1 is h plus v1, y2 is h plus v2, and so on, yn is h plus vn. And we assume in our analysis that h does not change with time. Okay. So here we have another assumption. What was the first assumption? The first assumption was that the distribution of V is Gaussian with mean 0 and variance sigma square, right? The second assumption is that all the VKs are IID, that is, they are identically distributed and they are all independent to each other. Now, what is the meaning of independence and what is the meaning of identical? Okay. Can go down. So identical. So identical means that all the yk have the same distribution 0, sigma square. That is, they have the same PDF. And independent means, so independent basically, if you see from a set theory perspective, the circles are not intersecting, right? That is, they are independent. Or from a mathematical perspective, f of, if you take the joint PDF, right? If I write it as, so the joint PDF is the product of individual PDFs. Okay, so this is the meaning of identical and independence. So what we are saying is that all the V's are IID, that is, they are identical and they are independent. And since H is constant with time, all the Y's also become IID. Okay. Fine. So now we have to find out the joint PDF of vector Y. What is joint PDF of vector Y? So this is what we need to find out. Okay. Just, yeah. So vector Y is represented as a column vector y1, y2, so on up to yn. And as we saw above, we use the identical and independence property to find out the joint PDF, which is the product of individual PDFs. If you multiply all the PDFs of Y, what was the PDF of a single Y? So PDF of a single Y we had computed above. So this is the PDF of a single Y, right? This is a Gaussian with mean H and variance sigma square. This is a PDF of single Y. And if you multiply these PDFs for all n samples, we get this mathematical expression. So this term before the exponential 1 by root 2 pi sigma square, it will be multiplied n times. And inside the exponential, right? So all the exponential degree terms will get added to each other. So you have k is 1 to n and yk minus h square. All right. So we move ahead. Now, you may remember base rule.
మేము చెప్పి ఇవి తెచ్చుకున్నాం.
So you may remember base rule. Now what happens in base rule? So base rule states that, and if you see, okay, let me go again to the motivation. So you are transmitting some signal H, and you are observing a vector Y, right? You are transmitting a constant signal H. So H is not changing with time, and you are observing some Y. You are sampling them. You are getting Y1 to Yn. Okay. So what does base rule say? So in base rule, the probability that you are transmitting H given you observe Y. Okay. What is the meaning of this? That Y is given. Okay. So we have Y with us. And what do we need to know? We need to know that H was transmitted, right? So H is being transmitted given vector Y. So this is what I require. Okay, so this is called the a posterior. And the probability that you observe Y, okay, given H was being transmitted. Okay, given H is transmitted. Now this expression P of Y given H is this expression. So try to understand. So in this expression, we know H is being, we know that some H has been transmitted, and we have this PDF. Okay. And what we need to know, we want the a posterior probability that what was transmitted is H and what we observe is Y vector. Now in base rule, you also have PH and PY. Okay. Now PH is called the prior. This probability of Y vector given H is called the likelihood. Now, since, as I said in the beginning, that currently we are assuming that H is time invariant. So H is time invariant. Hence, H does not have a probability PDF of itself for the current analysis. So since it is a simplified signal model, PH will not bother about PH currently. Okay. So what we want to know, we have to, so we need to maximize the a posterior, right? We want to maximize the a posterior probability, which is equivalent to maximizing the likelihood. Because H is deterministic, H is time invariant, so the prior probability of H does not arise. So we want to maximize this PDF, right? Now, okay, so we have to maximize this PDF. Now, to simplify our calculation, we take the logarithm, we take the natural log of this expression. So note that if you take the log of any expression, the nature of the expression won't change, because log is a monotonic increasing operator, right? So whatever is the nature of the original function, whether it is concave in nature or it is convex in nature, taking logarithm of any function does not change its nature at all, and it helps in simplifying the problem. Okay. So we compute the logarithm. So here L represents the log operator. So we take logarithm of the likelihood. So log a to the power. So you should know this, right? Log of a to power b is b log a. So we use this and we break the likelihood. And you should remember that we need to estimate h, which is the unknown parameter. Okay. So my original problem, which was maximizing the likelihood, is now has become maximizing the log likelihood. Okay. So maximize the log of likelihood. Okay. That is why this is also called a log likelihood estimator. Log likelihood estimator. So how do we find out the value? Very simple. We will differentiate the parameter we need to compute and equate it to 0. Right. So this is where we differentiate and we will equate it to 0. So when you differentiate the first term, this term, this is the first term. The first term does not have h, so it gives 0. The second term, if you differentiate, you get this expression. If you solve this expression, you get h is 1 over n summation of all yk, okay, which is h hat. So h hat. So we define a new variable h hat, which is the estimate of h, which is, so the numerator is the sum of all the observations which we sampled, right? And n is the total number of samples. Total number of observation samples, right? And what are the y's? The y's are the observation which you are seeing, right? So what are we saying? That if you are transmitting a fixed h, and at the receiver, if you're observing some random y's, right, then the expected value of this random fluctuation will be h hat. Okay, so this is what we are saying, right? So this is the average of observation. Okay. Any questions up to here? Right? No questions. So next we need to determine that how close is our estimate to the true value. Okay. How close is the estimate to the true value? How will we determine this? So we have two ways to check the closeness of estimate. First is the mean and second is the variance of the estimate. Okay. So just see this diagram. It should be more. So you are transmitting h, right? And now what I'm saying is that you are so your estimate of h is h hat. And now what we want to see is how close are h and h hat on the y-axis, right? How close is h hat to h? That is what we want to see. So first we compute the expectation of h hat. Expectation of h hat is 1 over n summation expectation of yk. I take the expectation operator inside. Okay. And expectation of yk, and we know that each yk is h comma sigma square Gaussian distributed. We saw above. So you will have summation of h, which is n times h, and n cancel out with each other, and you are left with h. So what we see is that expectation of h is h itself. When the expectation of estimate equals the true parameter, then the estimator is called an unbiased estimator. Okay. The variance. Okay. What will be the variance of my estimate? So as we did for the expectation, you take the variance operator inside and 1 by n square will come outside. So variance of each y is sigma square. So you have n sigma square divided by n square, and you have sigma square over n. So we compute that the expectation of the estimate is h and variance of the estimate is sigma square over n. And hence we see that h hat is Gaussian distributed with mean h, but now the variance is sigma square over n. Okay. So what we observe from this variance, that if my n increases, what is n? Number of samples, right? Then the variance of h hat will decrease. Okay. And if the variance of your estimate decreases, that means the estimate, that is the estimator will be as close to your mean of the estimate, which is the true parameter itself. Okay, so as n increases, variance of h hat will decrease and h hat will tend more and more closer to h, and sigma square by n will tend towards 0. So what you can also visualize, so if you have this PDF, right? So we are drawing the PDF of h hat. Okay, so PDF of h hat. So you have a Gaussian PDF, right? And its mean is h. Okay, so if its variance is very high, then so the spread determines the variance, right? And if the variance is less, then it will be more and more skewed towards the mean. Okay, so if I call this to be variance 1, and if I term this to be variance 2, right? Then variance 1 is greater than variance 2. Okay. So what we want, that the variance should be as small as possible so that my estimate is more accurate. So if I summarize, we transmitted a constant signal h. We transmitted a constant h. We observed some observations, right? Some random observations at the receiver. We sampled them, right? We had those samples. We observed that each sample is Gaussian distributed with mean h, variance sigma square. And you should note that you only have samples in your hand. Okay, you don't have any other information. You only have the samples, and yes, and you know that the distribution of V is Gaussian with 0 sigma square. You know this. This is the only two things which you have in your hand. And using these two information, you need to estimate h. This is your objective, right? And you need to estimate the true value. And this estimate comes to be the sample mean. That is why the more samples you have, the better is your estimator. And this estimate is observed to be Gaussian with mean h and variance sigma square over n. Okay. Any questions up to here? No questions? right? So we move ahead. Now, what is the optimum number of samples which you should have? Right? So here we discussed that you observe some samples, right? At the receiver, you observe some samples, right? So how many samples? Right? How much samples do we have to take from what we are observing so that the estimator gives a reliable estimator, right? So that the mean is so that the variance is sufficiently less and the expectation tends towards the true value. So how much samples do we have to take? That is the next question, right? So what is the n? What is going to be my n? Right. Now reliability. What do we mean by reliability? So reliability means that my estimate h hat should be as much possible, as close as possible. Okay, so 99.99%. Now you will ask why not 100%? Now, so as we move to week 2 and week 3, we'll see that there is a bound called the Cramer bound. So what is this Cramer bound? So Cramer bound is the minimum variance which you can achieve, which your estimator can achieve. So you will observe that the actual variance can never be zero. So sigma square by n can never be zero. Okay, so it will reach a lower bound below which it cannot go. So that is termed as the Cramer bound. We'll see in week 2 and or week 3, right? So fine. So what do we have? So we have the h hat, that is my estimate, which is Gaussian distribution with mean h, variance sigma square by n. We have this information, right? We derived earlier. Right. Now, what is the error in estimate? What is my error? H hat minus h. This is my error. Okay, fair enough. H hat minus h is my error. Now, if h hat is Gaussian with mean h and variance sigma square by n, then h hat minus h, what will happen? H hat minus h will be a zero mean Gaussian with variance sigma square by n, right? So, and further, if I want to convert this Gaussian to a unit Gaussian, what is a unit Gaussian? A unit Gaussian is a Gaussian which has mean 0, variance 1. Right? In that case, we will divide the variance. Then h hat minus h, we'll divide with the standard deviation, which is root of variance. Let's write that down. So standard deviation is root of variance. So what is my standard deviation? Is sigma square by n root. So this is my standard deviation. Okay. So h hat minus h over sigma by root n is a unit Gaussian, right? Okay. So let us denote this unit Gaussian by W. Okay. Fine. Now it is usually given in numericals. You must have seen that probability that your error is between some limit should have 99% reliability, right? So this is what we need to compute. So if we want to compute this, so what we'll do is we'll convert h hat, which was h gamma sigma square over n. We will convert it into unit Gaussian. Okay. In that process, what happens is, if so this is the absolute value of h hat minus h. Okay. So h hat minus h is less than equal to minus x to x. Okay. And so what we do is we divide h hat minus h with the standard deviation. So if we divide h hat minus h with standard deviation, then x also gets divided with the standard deviation, minus x also gets divided by the standard deviation. So now this is a unit Gaussian, right? This random variable is a unit Gaussian. And since it is a unit Gaussian, it will follow the Q function. Okay, what is the Q function? Okay, I'll just explain the Q function here. So Q function is called the, so this is called the tail probability. Okay, what is the tail probability? Let us just see that. Just a minute. So assume you have a Gaussian distribution. Right, this is a Gaussian distribution. Say you have any so this is spanning over some random variable x, right? So if I take q of x, okay, so what will be q of x? So this will be q of x. Right, so this is called the tail probability. Right, this is the tail. And since it is a unit Gaussian, okay, keep this in mind. This is a unit Gaussian. Okay, so it is a perfectly symmetric Gaussian. So if I take at minus x, right? So q of x equals q of minus x. This is only for unit Gaussian. Okay, for unit Gaussian, q of x is equal to q of minus x. How will you compute q function? There is a table. There is a q function table. So like you have a log table, you have a q function table also. Okay, so you can use that. And if you use, so okay, one more concept. So just a minute. Yeah. So probability that x is less than equal to x. This is my CDF, right? This is my CDF, cumulative distribution function. And this is equal to q of yeah, just a minute. This is equal to minus q of x. No. This is equal to q of x. Right. So when you have probability a, x, b, x is my random variable. B, A and B are my limits or boundaries. Right. So if you see here, then you can just consider, let's say this is A and this can be possibly B, right? So what we want, Q of A, that is this is Q of A and Q of B, and we have to subtract it. Okay, so if you subtract Q of A, and so this will be Q of A minus Q of B, and since it is a unit Gaussian, it becomes 1 minus 2 times Q of A. Right? And if you solve it, we get it. And also, if some of you may be interested to study this subject a bit deeper, I have written 2 references. SMK, Fundamentals of Statistical Signal Processing, Volume 1. This is a very good book for estimation theory. You can follow that. And Sheldon Ross, First Course in Probability. This will help you with some basics of random variables and probability if you guys feel some problem. Right. So fine. So any doubts? And then we'll move to problem solving. Any
Hello.
doubt? Yes. Yeah, you can speak.
Sir, actually, I'm just talking about the practically whenever implemented in MIMO in ODB, there is a multiple input and multiple output. Then whenever we are using carrier aggregation, there is some defects. We have found defect for carrier aggregation. So multiple carriers, the like sir, uh, CTA bundling, sir. Hello.
Yeah. So what is your defect?
Defects are generally users are not increasing.
Okay. Vishwajit,
What
we'll
was the
take.
cause? Yes, ma'am.
So we can take this discussion after I finish up with what I have to take, right? So we can take that after this session ends. Is it fine? So
Okay,
so
no
that
issue.
yeah, so that will be fine for everyone, right? So okay. So we'll just quickly go through the previous year assignment of week 1. Okay, so just a minute. Okay, so the first question is in view of, can you see or is it too small? Just a minute. So in view, in the context of estimation, the PDF of observation when viewed as a function of unknown parameter h is termed as. So we saw this right currently. So P of vector y given h, right? So y is a function of h, right? So if you can recollect, this is the likelihood. Consider. So now what is the next question? So we have a wireless sensor network. We are given the signal model, which is yk is h plus vk, and we have n number of observations. Okay, and it is given that the noise samples are IID. It is given they are zero mean Gaussian. Okay, and then the likelihood. So again, a very direct question. We had derived it back. So this will be yeah, it should be option B. If anyone has any doubt, you can just say, right? Okay.
No, sir.
Yeah, someone is trying to say. Yeah, go ahead, please. Yogesh, I think you're trying to speak. Yogesh, you can speak. You don't want to ask?
I have no doubts, sir. No.
Okay, you have no doubts?
Yeah, no doubt, sir.
Okay. Third question. In third question, consider a sensor network. It's the same signal model given. You have n observations. So what is the ML estimate of H? ML estimate of H is the sample mean, which we computed, right? So H hat is 1 over n y1 to yn. So this is my sample mean. We derived it earlier. Next question, you have again the signal model. You are given n observations. where IID. Now ML estimate is what, right? So just remember, this is ML estimate. How do we write? H sigma square by n. So it is unbiased, right? So expect what is unbiasedness? So expectation of H hat is H itself, right? So it is unbiased. Yes, it's unbiased. It is Gaussian distributed also. Yes, it is Gaussian. And the variance decreases by 1 by n. Yeah, so it is 1 by n times sigma square. So all of the above. Okay. Fine. Then you have again the same signal model. Now you have four observations, y1 to yk, and it is given sigma square is -6 dB. Now this I would like to clarify. So since sigma square is -6 dB, so you need to convert dB to watt. Okay, you have to convert it to watt. So if you take 10 log 10 sigma square is -6. Okay, so sigma square will be 10 to the power -6 by 10. And you need to use this value of sigma square in the um, uh, problems. Okay, so what is the ML estimate of H hat? So okay, so since H hat is 1 by n summation over yk, so you don't need the value of sigma square for this problem, right? So you are given the y's. So if you just add the y's, so it is 1 minus 3 plus 2 minus 1 and 4 is my n. So you have -1 over 4, right? So this is the answer. We move ahead. Consider a wireless scenario. You have the same signal model for 4 observations, and you have the observations which is y's. You have sigma square is -6 dB, and what is the PDF of H hat, right? So as we saw above, it is Gaussian, right? Okay. Fine. Then next question, question 7. It seems to be the same signal model again. You have the same observations. You have sigma square -6 dB. And what is the mean of the ML estimate? So the mean of the ML estimate is H itself. That is why it is unbiased. So this is the answer. Next question. It is again similar. Right? What is the variance? Right. So variance is sigma square by n. Note that this sigma square is not in dB. It is in watt. Right. So you need to convert this sigma square as I explained above. So 10 log 10 sigma square is -6. So sigma square in watt will be 10 to the power -6 by 10. You have to so this by 4 and you will get the answer. Okay. Next question. So right. So okay. So you have the observations and probability that H hat lies within a radius of 1 by 2 of the unknown parameter. Okay. So this is probability that H hat minus H lies between 1 by 2. Okay. So remember what we derived just a few minutes ago. So what will happen is, so this can be written as probability minus half H hat minus H half. Okay. Do remember that H hat was Gaussian H sigma square by n, right? So H hat minus H is Gaussian 0 sigma square by n. So we have removed the expectation, right? Expectation is 0, but the variance still remains. The variance still remains. So this is very important. So you need to convert this into a unit Gaussian, right? So H hat minus H divided by root sigma square by n, which is your standard deviation. So you need to divide it by standard deviation. In that process, minus 1 by 2. Okay, what is the standard deviation? So the standard deviation was computed for this question. Okay, this comes out to be 1 by 16. If you solve this comes out to be 1 by 16. Okay. So you need to divide this throughout by the standard deviation. So if you divide it throughout by the standard deviation, so you will have 16 by 1 h hat minus h over 1 by 16, 1 by 2, 16 by 1. So this is probability minus 8. And this is your unit Gaussian. I'm just representing it by W 8. So this will be Q of minus 8 minus Q of 8. This will be 1 minus 2 Q of 8. Have we committed some error somewhere? Let's check. All right. So right. So here this was root of sigma square by n. Okay. So if you take the root of sigma square by n, so this will be so root 16 is 4. Okay, and 4 by 2 is 2. So this is minus 2. Similarly, here you have 4 by 2 is 2. So you have q of minus 2 minus q of 2, which is 1 minus 2q. Okay, so 1 minus 2q. This is a very interesting question. So now it is given that the noise samples are Bernoulli distribution. Okay, so you have Vk belongs to 0, 1, and okay, let me just write this. So we are given that Vk belongs to 0, 1. Okay, and probability that Vk is 1 is P. Probability that Vk is 0 is 1 minus P. Now we know this. Okay. And Y is H plus Vk. So what will happen? So note that Vk can be 1 or 0. Okay. So if Vk is 1, then what will be Y? It will be H plus 1. Right? If Vk is 1, and it will be H if Vk is 0. Okay. So Yk can only take two values. It will take with the probability of 1 minus P, and it will take 0 with probability P. Right. So if you have 2 Yk to observe, right? If you have 2 Yk to observe, then the minimum of the 2 Yks, right? So what will be the minimum of H and H plus 1? Right. So it will be H. So H will always be lower than H plus 1, right? So by that intuitive logic, minima of Yk is going to be your maximum likelihood. Okay. So this was the last question from my side. So yeah. So any questions in the any doubts on the numericals which we have done? Anyone?
Sir, I am Manish Sharma. Please show the first question again, please.
Okay. Right, Manish. Yeah, you have question 1.
Okay,
Yeah.
sir. Okay, thank you.
All right. Any conceptual doubt or any other clarifications? No? All right, so I am stopping the recording. And,
and this recording will be